So in the last lecture we have seen the successive over-relaxation method as a simple means of increasing the rate of convergence over Gauss-Seidel method for the specific case where A is diagonally dominant. We made the point that the optimal SR can have tremendous increase over the Gauss-Seidel method because it would take only square root of n number of arithmetic operations for in terms of the asymptotic rate of convergence as opposed to n for the Gauss-Seidel method. Therefore, the total number of arithmetic operations varies as n raised to power 1.5 compared to n square for the Gauss-Seidel method. When n is large, that is when the number of grid points is large, then the variation of n to the power 1.5 or n square can make a huge difference. But this kind of great improvement is possible only for the case where we have the optimal SR parameter, optimal value of the SR parameter, and that is something that is not known in the general case. So we have to keep that in mind and then try to estimate the value of the optimal value and then see how it can be how the rate improves. There is a different approach for acceleration of the solution of Ax equal to b, and that method, one such method which is known as the alternating direction implicit method, is what we will examine in this lecture. The original form was proposed by Peaceman and Ratchford in 1955. It is a combination of the iterative method and the direct method. Specifically, it takes advantage of the goodness of the tridiagonal matrix algorithm, goodness in the sense that it takes only n number of k times n number of arithmetic operations to get a solution of Ax equal to b, where A is tridiagonal. Okay. So it takes advantage of that, but it puts that in the context of an iterative method, and we will see that for the specific case of elliptic partial differential equation in Cartesian coordinates with Dirichlet boundary conditions and 2D problem, which is written in this rather unfamiliar but more generic form, where you are writing it as dou by dou x of A, which can be a function of x and y, dou u by dou x, plus dou by dou y of another function c, which can again be a function of x and y, times dou u by dou y, plus g times u is the unknown variable here, like our phi, g, which is again a function of x and y, equal to s, which is a function of x and y. So this is a generic elliptic partial differential equation in Cartesian coordinates in 2D, and A and C have to be positive functions for the equation to be elliptic. So if G is assumed to be non-negative, and considering a uniform mesh spacing of h and k in the x and y directions, this equation can be discretized as h plus v plus d times u equal to q, where h, v and d are operators. So you have hu equal to something is given by minus a x y times u at x plus h times y plus 2b times xy times u at x y minus c x y times u at x minus h y. Okay. Now this looks a bit complicated. Essentially what we are using is central differencing here, and so this becomes u at I plus 1, and that is what this is, x plus h. H is the delta x equal to delta x here, and k is equal to delta y. It is just a unfamiliar notation, and one would say that it is nothing but central differencing in a slightly different disguise. And I would like to mention the point that sometimes we have to go into unfamiliar territory, and if we work it out by ourselves, then it actually enables us to look at what somebody else is saying and it helps us understanding what somebody else is saying, maybe in a slightly different language, and we should always be receptive to those kind of ideas from other people who may not speak in the same language as us. So in that sense, that's why I put up so as to build character, and so I'd like you to just follow it up and see that this is nothing but central differencing and applied where, since your a and c and also g and x are functions of x and y, they take they can vary here, and that's what this is saying. And but what you have in HU is variation with respect to x. So you have u at x plus delta x, u at x, and u at x minus delta x. Similarly, v u, h is for the horizontal and v is for the vertical. So horizontal meaning x variation and v vertical meaning y variation. And similarly, we can see that vu is u at x y plus k, so that is y plus delta y, and again you have y minus delta y here, and then you have u at y. So this is u at I plus 1, ij plus 1, u at ij, and u at ij minus 1, and you have corresponding coefficients here, because these coefficients are variations of x and y. You also have this, and du is hk times gxy, so that is coming from here, and q is coming from here. Okay, so q is the right hand side term, d is a diagonal term which involves the value of u only at ij point, and so that is given by this one here. So when you put all these things together, then you can put it in this particular form. So a is k times k divided by h times a at x plus h by 2, so that is a at I plus half j, and c is I minus half j, and d is I j plus half, and e is I j minus half. So in our notation, these are all fairly simple things to follow, and we can write it like this, but we would like to have the practice of doing it in a different way, and that's how we have put it. There is also another reason for doing it, that is, we have the general case and we have not assumed these to be constants, and general case can give us can extend our range of applicability. Okay. So what we have done so far is nothing but discretization of our elliptic equation, a general form of elliptic equation in Cartesian coordinates. So that's our equation here, and Peaceman-Rashford proposed a two-step solution for the case where g is equal to 0 and d is a constant tau I. Okay. So this discretized equation of h plus v plus d times u equal to q, they propose to solve as two separate equations in a two-step process. As you go from n to n plus 1, you first evaluate u at n plus half by taking the horizontal derivative and a constant tau 1, and vertical derivative is evaluated at nth value, and horizontal derivative is evaluated at n plus half. Okay. So this will involve, for example, the first equation will involve u at I plus 1 j, u at I j, and u at I minus 1 j. Okay. So that makes it implicit in x direction, all values giving us at n plus half. Okay. And this part, which is v u n, are the y derivative terms coming in this, and these are being evaluated explicitly. So the first equation is implicit in x but explicit in y, and having done this, having evaluated the x derivatives at implicitly at x plus half at n plus half here, you now come to the vertical derivatives. So these are evaluated as implicitly, because v u n plus 1 will be uij plus 1, uij and uij minus 1, all these things are evaluated implicitly, because that is how we have put it as un plus 1. And here we have h derivatives also contributing to this, and these are evaluated at the latest values that are available here. So that is h un plus 1 n plus half. And what we note is that the right hand side terms can be evaluated because these are in the previous time step or previous half time step values, and only the left hand side terms are implicitly evaluated, and the first equation evaluates implicitly the derivatives and variations coming in the x direction, and the second one takes care of the variations in the y direction. Okay, but since each time we are only considering one dimensional variation, so that is at best dou square u by dou x square here and dou square u by dou y square here, we have a tridiagonal matrix for each of these. The tridiagonal matrix represents, in the first case, the second derivative and other variations in the x direction, and in the second case it represents the variations in the y direction. And this is also such that we can get diagonal dominance, so we can make use of TDMA scheme. And since as we go from iteration n to iteration n plus 1, we first evaluate the derivatives in the x direction implicitly, and then we evaluate the derivatives in the y direction again implicitly. This is called an implicit method, and alternating direction implicit, because you are alternating in x direction and alternating and then in y direction before you complete the step from n to n plus 1. Okay. So that is why this is alternating direction implicit method. The scheme is expected to be faster than Gauss-Seidel method, but not as fast as the optimal SR method. Okay. So in the specific case where the operators h, v and d commute, so that is h v equal to v h and h d equal to d h and d v equal to v d, okay, which also essentially means that if a of x y is just a function of x and c of x y, which is coming in the y derivative term here, if that is only a function of y here, and g of x y, which is coming here, is not a function of x and y. Okay. So in this particular case we can get much faster results than approaching, in fact even better than the optimal SR methods, and I would like to refer you to the book by Axelson. It's a mathematical book. Okay, it's mathematics based book, and in this condition, when you have this kind of commutativity of the HVD operators, or if you have your equation in which a is a function of x only and c is a function of y only and g is constant, then in such a case it is possible to generate a series of numbers tau 1 and tau 2 such that you have an asymptotic rate of convergence which is of the order of log h inverse 1 compared to h inverse 1. Okay. So it is 1 by delta x here, and this is 1 by log of 1 by delta x. Since this variation is smaller than this variation, we can get much faster rate of convergence than in the case of Gauss-Seidel method or optimal SR method. And what this functional variation, where a is a function of x only and c is a function of y only, makes the equation here like a variable separable. The solution is like a variable separable type of format. So if you have that kind of elliptic equation with an arbitrarily complex variation of a in terms of x, okay, which makes the solution probably more difficult analytically. So if a is a function of x only, but it can be any complicated function, and we are evaluating it numerically, so there is no problem here. So when we look at the numerical solution here, we are going to evaluate the small a, in which a functional form is is evaluated numerically. So it can be any kind of arbitrary complexity in X only. So, in such a case we can get tremendous rate of improvement of the alternating direction implicit method over the Gauss-Seidel method or even optimal SOR method. Okay. So, we can generalize this ADI method. Okay. If you take Ax equal to b and decompose it into A1 plus A2, then we can put it in this particular form, where 1 plus tau 1 A1 x n plus half equal to 1 minus tau A2 x n plus tau 1 b, and 1 plus tau 2 A2 x n plus 1 equal to 1 minus tau 2 A1 x n plus half b. Now what this one is saying is that this A2 part of this is being evaluated explicitly and A1 part of this is being evaluated implicitly. Okay. And having done this, now you come to the other part A2, which is being done explicitly in the implicitly in the second step of the equation, and A1 part is now being evaluated explicitly. Again, if you do this in the case of stationary ADI, so that is tau 1 and tau 2 are constant, they do not change from iteration to iteration, and if this decomposition is such that A1 and A2 are positive definite, then the method would converge if tau 1 and tau 2 are positive, and if A1 and A2 and commute, then a sequence of tau 1 and tau 2 can be generated to give a fast convergence rate. So, these are the idea here is to say that there is no one approach to the solution of Ax equal to b. Okay. So, the idea here is not to say that this is the method by which we can solve. There can be different approaches for different things. When a mathematician looks at Ax equal to b, then he will see many possibilities, and in some cases if we are aware of those kind of possibilities, then we can take advantage of that and then get to a solution. And sometimes when we, by looking for alternative ways of getting a solution, we may get some specialized method which will apply for special class of problems. So, it is in that sense we would like to have a background to the solution of Ax equal to b, and it is not a trivial problem, and people have had spent their careers trying to look for various methods, and this module is just it is an important part of CFD solution. And so, this module is looking at how many different ways or what are the different kinds of successful approaches that people have adopted for the solution of Ax equal to b. So, it is in that context we are looking at it, not in the sense of trying to solve our simple problem. We are trying to get a good view of, good perspective of the field of CFD from, especially in the context of solution of Ax equal to b, which we realize is a very important problem when we have large number of grid points, which we need to have in order to get confidence in our CFD solution. Okay. So, it is in that context I am putting this up, not from an examination point of view, not from a solution point of view for a specific problem, but as a general matter of academic significance. Okay. So, we can extend the ADI method even for parabolic equations, but we have to do it in a careful way. So, let us consider this parabolic equation where you have dou u by dou t equal to alpha dou square u by dou x square plus dou square u by dou y square, and this is an unsteady two dimensional problem with constant alpha. Earlier in this case we have put some diffusivity which is spatially varying here, and here we are looking at a constant alpha which is the same in the two directions. We can use our implicit FTCS differencing for stability. We know that explicit means that there is conditional stability, but implicit will make it unconditionally stable, but in the process we get an equation which has 5 diagonals, and 5 diagonals means that we cannot solve it using the TDMA method. Okay. So, now in order to bring in the TDMA possibility, we would like to pose it in this particular form where we take only the x direction and only the y direction variables. Now, how can this be done when we have this time derivative also? So, for that we write it symbolically as un plus 1 minus un equal to delta t times Sx plus Sy times un plus 1. So, Sx and Sy are operators in the sense that you do not have Sx without u. Okay. So, we define Sx un plus 1 as alpha by delta x square, un plus 1 which is the time index, and with subscripts I plus 1j, u ij and u I minus 1j. So, this whole thing is representing dou square u by dou x square, and the right hand side is being evaluated at n plus 1 time step. So, in a way we know the difference between explicit and implicit, and this is an implicit way of dealing with the space derivative, because your time derivative involves this un plus 1 here, and so when we put this, evaluate this at un plus 1, this makes it implicit, and that is why we call this as FTCS implicit. And similarly Sy un plus 1 is now taking care of the y derivative alpha by delta y square, u I j plus 1 minus 2 u I j plus u I j minus 1. So, in that sense this is again like what we have written previously in a straightforward way for FTCS implicit. Now, we are putting it in more symbolical language, and once you put it like this, you can bring in the operation, we can club this operation of un plus 1 with this and write it as 1 plus, there must be a minus here, okay, 1 minus delta t Sx plus xy un plus 1 equal to un. Okay, we take this onto the other side, we bring this onto this side, and we will be getting 1 minus here. Okay, so now we can split this thing here into 1 minus delta t Sx times 1 minus delta t Sy times un plus 1. This is the full expansion of this, and because this is delta t square and these are delta t, we can neglect this as a higher order term, and then we can write this as 1 minus delta t Sx times 1 minus delta t Sy times un plus 1. Okay. So, now we are writing this one with a minus sign here as 1 minus this and this. So, now this equation, this being made equal to un, can be solved in two half time steps, each 1D with the possibility of use of TDMA. So, we can first write this as 1 minus delta t Sx un plus half equal to 1 plus delta t Sy times un, and from this we get un plus half, and we substitute this here, and then we solve for 1 minus delta t Sy un plus 1 equal to un plus half minus delta t Sy un. Now, what we claim is that this solution here, this two step solution here, is the same as the solution of this, which is roughly the same as the solution of this within second order accuracy in time. Okay. Now, we are using here this discretization is first order accurate in time. So, the second order terms can be neglected with respect to the first order terms here, and that is the argument here. So, this decomposition into two independent steps of this one here is the same mathematically. And how can we do that? We can do that by substitution. We can pre-multiply this by 1 minus delta t Sx, and then we can substitute this expression here and show that this is the same. So, it is a bit of exercise that I would like the interested reader to pursue, and to show that this is equal to this one. So, there is a pre-multiplication of this one by 1 minus delta t x, delta t Sx, and then substitution of this this thing here with this will actually give us this solution here. Okay. Now, what is the advantage that we have gained in this? we can write this equation as un plus half ij minus beta x, where beta x is alpha by delta x square, the alpha delta t by delta x square, which we have seen in simple differencing of this using FTCS implicit. So, this is minus beta x times u n plus half I plus 1 j minus 2 u n plus half I j plus u n plus half I minus 1 j equal to u n I j plus beta y times u I plus I j plus 1 n minus 2 u I j plus u n I minus 1 j. So, this is the term that is coming here, and this is already known from the previous value. So, all the right hand side is known, and the left hand side involves I plus 1 j, I j and I minus 1 j, and you also have I j term coming here. So, this gives us a tridiagonal matrix, and this can be solved using TDMA scheme to get u n plus 1 at all I j, okay. And this we bring in here, and then we write the second part of this equation here to get u n plus 1 now at I j plus 1 and I j minus 1. So, once we solve this equation, then we get u n plus 1 I j at all points. So, this is again a tridiagonal matrix involving u values at n plus 1 time step at I comma j for all of them, and this involves again a tridiagonal matrix, but involving u at n plus half time step, not at n. So, this 2 time step solution enables us to break up this pentadiagonal matrix into 2 tridiagonal matrix solutions. Now, this pentadiagonal matrix is not 5 adjacent diagonals, but this is with 5 diagonals with some zeros in between. Okay. So, this particular decomposition of this scheme into this is unconditionally stable for transient diffusion. Even in 3D we can extend this to 3D and have 3 successive 1D solutions, but the stability is guaranteed for transient diffusion. But if you bring in some advection terms into this, then we have to look for stability and we have to see whether it is stable or not. So, for the general case where you have other terms that are coming, then we have to look at the stability. But otherwise, this breaking up of essentially a pentadiagonal matrix into 2 tridiagonal matrices or a 7 diagonal matrix for the 3D case of this transient diffusion problem into 3 1D problems is unconditionally stable, and we can just go ahead and get a solution for this. And the overall scheme is expected to be faster than trying to use Gauss-Seidel method for the same pentadiagonal or 7 diagonal equation. And so, this is an innovative way of making use of the goodness of the tridiagonal matrix algorithm for the solution of a matrix which is not tridiagonal. But what this also tells us is that it is not a trivial extension. We cannot just take it up into anything. We cannot factorize it and then take it up. This is part of the operator splitting kind of approach, and it has to be done properly. And what we would like to show here is that this problem broken up into written up in this way and approximated as this way, and then this is equal to un. Okay. So, that problem is broken up into 2 steps which are given by this, and this breakup is such that this resultant problem is given like this. For example, why we are writing it like this and why we are writing in a different way here is part of the decomposition of the problem. Only doing it this way will mean that this 2-step solution is the same as this 1-step solution. Okay. So, we would like to be aware of this, that it is not a trivial solution, it requires some thought into the proper decomposition, and in the general case it requires also stability analysis. So, with this we would like to conclude this presentation of this alternating direction implicit method. This is, as you can see, is a different approach to accelerating the solution over the Gauss-Seidel method, and the solution in this particular case is trying to take advantage of the fastness of the tridiagonal matrix algorithm. Okay, but this has this works only in certain cases in a straightforward way, and even then we have to be careful about the decomposition. Okay. So, in the next lecture we will look at yet another way of accelerating over the Gauss-Seidel method, and this again looks at it incorporates a different philosophy. Okay. Different philosophy in the sense that any iterative method like solving Ax equal to b as an iterative method like this, the convergence of this iterative method is faster if the breaking up of A into m and n, okay, we are putting x equal to m and n here, and part of this m is being evaluated in an implicit way. So, the idea we will introduce in the next class that if m is very close to A, then this becomes a solution which is implicit. So, the idea of making, okay, we cannot take a fully implicit solution of Ax equal to b because that would involve n cube number of mathematical operations. But if we can do it approximately but as close to a fully implicit method, then we get a faster iteration, faster convergence, is the idea behind the strongly implicit procedure method, which we will see in the next class.